Welcome to our lecture on internal model control, which is from chapter 7 in the textbook. So the idea behind internal model control is shown here. And the basic principle is that we have a process model that's being solved simultaneously with the actual operation of the process itself. Now, when you hear terms related to smart manufacturing, that's often known as the digital twin. You're doing a simulation in real time of the process that's actually being operated. So in this structure, we have an internal model controller. The output of that controller changes the manipulated input to the process and then simultaneously changes it to the simulated process model, which I'm represented as GP squiggle. The actual measurement from the process is denoted Y, but the model predicted output is Y squiggle. The differences between the measured output and the model predicted output is what is sent back as an estimated disturbance back to compare with the set point, and then that modified set point is sent to the internal model controller. So you can see in this screen that I'm representing the process as the plant equipment. That is, this is what's really happening. This is what's underneath the insulation, the real operating equipment. And then what we have going on with the rest of the diagram is actually what's going on in the computer. So that includes both a simulation of the process model, and it includes the implementation of the controller that provides the control action and changes the valve or flow rate that's affecting the process. So the point is, the model and the controller reside in the control computer. Okay, so now we're showing this in total, where I've got the blue representing the process, and what's inside the dashed lines is representing the control computer, which includes the model being solved at the same time. Okay. So now we need to think about how we actually design that internal model controller that we're calling Q, so it's not confused with our classic feedback controller. We normally call that G sub C. And so what you're trying to do is think about the best possible scenario. Let's say there's no disturbances entering the process. So this term D is equal to 0. And let's further assume that the process model perfectly characterizes the behavior of the process. So that is, the model GP squiggle is equal to the actual process transfer function GP. All right. So in the limit of that being true, with no disturbance coming in, that means our model predicted output is going to be equal to our measured output. So that means this signal here on the diagram that compares the measured output and model predicted output is actually going to be 0. So then that means this equivalent block diagram, since there's 0 being fed back to the set point, can be represented in the limit of no disturbances and a perfect model as the following: the combination of the internal model controller Q and the actual process GP. So that in this particular scenario, the output to a set point change R is simply going to be the process transfer function times that controller Q. So in the limit, what if we could just say that Q is equal to the inverse of the process? So that's Q is equal to 1 over GP, and then that would tell us that the set point is equal to the output, or the output is equal to the set point. So you can perfectly track the set point. Now realistically, again, the controller has to be based on the model, which is GP squiggle, but again, we've assumed the limit that you have a perfect model, and so therefore GP squiggle and GP are equal to each other. All right, so in this scenario, the controller is the model inverse that I'm showing here. And so as you march through this step by step and assume that you have a perfect model, this means that indeed you could possibly track that set point perfectly. Well, in reality, this is not possible, okay, because that controller is not physically realizable. If we take the first order example, where Q then is the inverse of a first order model, that means you've got a higher order numerator than denominator. It's first order in S divided by 0 order in S, and that actually is not physically realizable. Okay, so then to make it physically realizable, we have another step. Let's take the inverse of the process model and then cascade that with a filter. And this is like what we assumed when we went through the direct synthesis procedure and we said, well, we want a response that looks like 1 over lambda s plus 1. So that would be a scenario where this n term, the exponential, is equal to 1. So let's think of a problem that's very challenging. We already know about right half plane zeros causing inverse response. So here's an example of a process model that has a right half plane zero indicating wrong way or inverse response behavior, and then second order in the denominator. So if we simply took the inverse of that process, then you flip the denominator and numerator, and this becomes the controller, then cascaded with that first order filter. So therefore, your controller Q would be second order divided by second order. Unfortunately, in this case, the controller would be unstable because you have a right half plane pole at positive 1/9. And so if you implemented something like this, you may think that you're doing a good job of tracking the set point. You've got this desired first order response, 1 over lambda s plus 1. But unfortunately, because the controller is unstable, it's actually giving you more and more control action. And in practice, you'd reach some limit. You can't actually implement something that's going towards minus infinity. So an unstable controller is something that we do not want to have. Right? So the way around that is to do a factorization of the model. And by factoring the model, what we mean is we're going to have bad stuff, GP plus, and good stuff, GP minus. And the bad stuff is going to be anything that we can't invert. That would be dead time, and that would be right half plane zeros. Because if you invert a dead time, that implies that you're predicting something. And then the right half plane zeros would cause an instability. But we still want to make certain that we have a gain of 1 so that when we have the overall multiplication of the bad stuff times the good stuff, we end up with the same gain as the original process model. Right? So the good stuff is going to have everything that can be inverted. It's going to have your stable poles, stable zeros, and it's going to have the actual gain of the process model. So if we take this particular example, and let's say we also have a dead time of 4 minutes. So we have a process model that has inverse response. It's got the positive 1/9 as a value of the 0. And it has a dead time of 4 minutes. And it's second order. Well, the way we might factor that is to take out the bad stuff, put that in the right half plane 0 in the bad stuff, and the time delay is in the bad stuff. And then the good stuff would simply be just the second order, and this is a gain of 1, so it'd have a gain of 1, and then the 15s plus 1, 3s plus 1. All right. Now, it's beyond the scope of this course, but there's another way to design a filter, and that would be, in addition, in the bad stuff, if you put a reflection of the right half plane 0 and made a left half plane pole, put that in the bad stuff, then to be consistent and make certain your overall transfer function remains the same, you have to have that same pole be a 0 in the good stuff. So when you multiply the bad stuff times the good stuff, you still get the original process transfer function. All right. So the procedure then is just to invert the good stuff, the GP minus, cascaded with a filter to make it physically realizable. In this particular case, then we're inverting the good stuff on that previous screen. Remember the previous screen we said we had 9s plus 1 over 15s plus 1, 3s plus 1. So we're taking the inverse of that. The denominator becomes the numerator and vice versa. And since this is second order, we need a first order filter in order to make this controller overall second order divided by second order. All right, so that controller Q consists of the inverse of the good stuff times this filter here. So that's what I'm showing as the Q. What I have behind this red bracket is the Q. All right, so if I insert that here for the Q, you notice you get the process times the inverse of the good stuff times that filter times the set point change. All right, and then so one key is when you do that, what you notice is if you break this transfer function into the bad stuff and the good stuff and assume the limit of a perfect model, then what you get is this expression shown here. And the key is the inverse of the good stuff times the good stuff. That's all equal to 1 then. And so what you get in your response is going to be the bad stuff times that filter times the set point change. Right? And so that means that when you've got time delays and when you have right half plane zeros or inverse response, then they must appear in the output response when you make a set point change. All right, so going back to that original example, what you're going to have in terms of the response to a set point change is you're going to end up with, in the closed loop, again, the limit of having a perfect model, you're going to get the inverse response, you're going to get the time delay, but it's going to be a stable response. Essentially, you've got the inverse response that's first order, and then you've got second order behavior. And as you make lambda smaller and smaller, you're going to get a faster response. Now, we mentioned a first order filter, and that's fairly standard when we're worried about set point tracking. There are other forms of the filter. We'll tell you in specific examples which one of these forms that we may want to use. If we're dealing with a batch system, we want to track ramps rather than steps, we may have this type of form. If we have an integrating process, we might have this type of form. And then we'll show a specific case where you may want to have improved disturbance rejection, and we'll have the form shown as the last filter design. So to summarize the design procedure, you develop a model, GP squiggle, you then factor it into the bad stuff and the good stuff, where the bad stuff contains the right half plane zeros and time delays. Then for the controller design Q, you only invert the good stuff of the process model, and you use a filter, which is often first order, to make that controller Q realizable. And again, that filter often looks something like this, particularly if you desire to make good set point changes. N is selected to make it physically realizable, but in the examples I'm using today, N happens to be equal to 1. Now you do the controller design this way, assuming a perfect model, assuming no disturbances, but then you actually have to implement it in the form of the IMC block diagram to account for model uncertainty and disturbances entering the process. So this is the form that we started out with. Again, we've got Q, the internal model controller. We have the actual process. We have the process model, which we assume the process and the process model were perfect when it comes to control system design. But as you know, you never have a perfect model in the real world, so you would still implement it in this form where you have the real process, that is the plant you're trying to control, and then the model that's being solved in real time, say the digital twin in parallel with the process. Now we can rearrange this though to look more like our classic feedback form. If we just take this comparison of our measured output Y with our model predicted output Y squiggle, if we move that junction point over to the other side of the diagram, we've only made a cosmetic change. This is still the exact same computation that's going on, and the signal that ends up being sent here is the difference between the measured output and model predicted output. So then the next step that you can do is actually take that junction and do some algebraic manipulations and bring it after the set point is compared with the measured output Y, and then that looks like this diagram here. Right? So what I have inside the dashed line includes the internal model controller Q, and it includes the model of the process GP squiggle. But if you just kind of block this out, you'd recognize that what's inside this dashed line actually looks like the controller GC. So this would be the feedback form, where now we are comparing the set point and the measured output, and then what we have right here would actually be the error signal be entering this dashed line block. So we can think of that as being GC. And so what you're going to find is when we implement this for different forms of models, it'll often be PID equivalent. Okay, so for simulations today, I created a live script imc.mlx, and it calls lec11_block.slx, and it does it for this particular plant, the one with inverse response and a dead time of 4 minutes, and then second order with time constants of 15 minutes and 3 minutes. And so inside the controller, the GP squiggle, when we have the case of having the perfect model, again, this is the representation of GP squiggle, and our controller design then just takes the good stuff, inverts it, and uses this first order filter. So when you look at the block that I put in to represent the internal model controller, then you can see that I've put in certain parameters to represent the numerator Q, where Q is the IMC controller, denominator of Q, and then the model numerator and model denominator, and then the dead time of the model are all entered in this block. And actually, what I do is I enter those into the live script file so that that gets entered into this block before the simulation is actually performed. Now here I also have the representation of the numerator of the process and the denominator of the process. And note that I want to be able to deal with the case where you actually have model error. So that's why the plant is represented by num_p and din_p, whereas the model I've called mod num and mod din, so that the numerator and denominator of the model may be different from that of the actual process. Then finally, I've got the transport delay that's associated with the process. Here I'm calling that theta p. All right, so what is inside this internal model controller block is what I showed several slides back, where I've got this internal model controller Q, and I've got the process model and the time delay that's in the process model, and that goes through this signal flow diagram. And so we have our measured output that's being compared with our model predicted output, and that's being sent here. And so the error signal is really built inside this block diagram, and this is the block that you actually see externally when you view the Simulink model. So please work through the MATLAB live script imc.mlx, which is calling lec11_block.slx, and basically I will have some questions on the next quiz that are related